Today's lesson is going to be on conservation of energy. We're going to basically be applying conservation of energy to calculate initial or final energies and thereby calculate change in heights or velocities as necessary. First off, we should be aware of the conservation of energy. In the sense that energy is only transformed from one type of energy to another type. We do not create or destroy energy. And in particular, we're going to be focusing on potential energies being converted back and forth to kinetic energy. We'll also be looking at forces that are internal to a closed system. These forces are responsible for transforming the energy from potential to kinetic. Forces that will be external to our closed system, basically applied forces or friction, those will add or subtract energy from our system. So I want to introduce the concept of total mechanical energy. Total mechanical energy is going to be the kinetic energy of a system, a collection of objects, remember, plus all the potential energies of the system. And as long as it's a closed system, which means no external forces, this will stay constant. So my total mechanical energy is going to equal kinetic energy plus all the potential energies, whether it's gravitational or elastic or when we encounter it, electric. Those are all energies that feed into my total mechanical energy. Work from forces that are external to my system, the applied force or friction. These types of forces will effectively take away or add to my total mechanical energy because they are external to my system. So my formula changes a little bit in the sense that my total mechanical energy plus my external work, which I add to it if it's a force in the direction of displacement, is going to equal my final mechanical energy. If my external work takes energy away, work external will be a negative value. The primary tool that we're going to use to help us apply conservation of energy is what I call an LOL diagram. This diagram helps us to analyze the energies in the before and after and any external forces doing work in our system. And this is what an LOL diagram looks like, It's basically a bar chart of the energies before. It doesn't have to be exact, but we need to label which ones we have. And then we have a bar chart of energies after a situation occurs, In the middle, in the O, basically what we list is any forces that are doing work or stealing work from our system. In the middle, we list our system objects, So over here, we would have a bar chart for kinetic energy, a bar chart for gravitational potential energy, and maybe one for elastic potential energy. And if it's something falling, I basically have, let's say I have 3 units of gravitational potential energy. And at the end, I would more or less have the same. And let's say it just falls. And so I now have 3 units or the same value for my kinetic energy and no gravitational or elastic at the end. So in the middle, in that O section, internal forces are only going to be capable of transforming energy. For example, the force of a spring, when the spring is in my system, that's an internal force and it transforms elastic potential energy into kinetic energy. I don't need to worry about the force of the spring. Similarly, most of the time we are going to include the Earth in our system, because the force of Earth's attraction or gravity transforms gravitational potential energy into kinetic energy. I don't need to worry about the force of gravity. So here's an example. I have a ball that is kicked horizontally at a speed of 5 meters per second off an 80-meter building. What speed does the ball have just before landing? Notice I use the word speed and not velocities. Since it's speed, I don't need to focus on direction or x components or y components. I'm just looking for the total magnitude of my velocity. So here's my LOL diagram. In the beginning, I have a little bit of kinetic energy, yes, because I have an initial speed of 5 meters per second. So yes, I do have some kinetic energy. have a lot of gravitational potential energy. Okay, let's say I have 3 units. Okay, I'm going to leave out the elastic because that's not going to be useful. In the system, I basically have Earth and ball. Okay, because that's really the only thing we're going to be focusing on. Okay, the Earth is the only force that's going to be in operation here, the force of gravity. At the end, okay, just before it lands, okay, my kinetic energy, I have a lot of that, okay, 5 units, because I have no gravitational potential energy just before the ball lands, okay. So that's how my LOL diagram works, okay, just to identify what energies I have. From there, we can start filling in numbers for it, okay, because in the beginning, I do have 1/2 mv squared, and I have mgh, and that's going to equal, because I have 0 work, no external forces, is going to equal 1/2 mv final squared. Okay, and I look at this and I realize I never gave you the mass of the ball. Fortunately, when I look at this, my m's cancel everywhere. Okay, so I can now stick in 1/2 5 squared because that was my initial. G I'll use as 10. H is 80. And that's going to equal 1/2 V final squared because that's what I'm looking for. Okay, so this becomes 800 plus 12.5 equals 1/2 V final squared. And when I plug this in to my calculator, I'll get a nice number. Let's see. And so V final squared is going to equal 1,625, and V final is equal to 40.3 meters per second. Okay, I don't know exactly what components are. I could potentially figure them out, but I didn't ask for that. And so this is how we can apply conservation of energy. Similar to the way we applied conservation of momentum, we figure out my energies in the beginning and my energies at the end. Are there any impulses, or in this case, is there any work being done on my system? In this case, no. Okay, and then we just solve as necessary. Okay, here's another example. Okay, I have a pendulum of length 1 meter that's released from rest at a height of 2 centimeters, 0.02 centimeters above its lowest point. Okay, so let's draw a picture for it. Okay, it's 1 meter, and I really think I meant 2 centimeters. So I basically have moved it over, and it is now 2 centimeters higher than it started. Okay, and it's released from rest. Okay, so calculate the speed of the pendulum at the lowest point. Conservation of energy is great for calculating speed. Not so great for calculating velocity because energy is a scalar. But in the beginning, I'm going to have GPE, but no KE. Okay, and at the end, at the bottom, my GPE will be 0, and my KE will have a value. So really, I have 1 unit, not a lot, and at the bottom, I'll have that. Okay, the string, at this point, the string is part of my system, and it is responsible for turning the force, not for speeding it up. Okay, so the string is always going to be perpendicular. Okay, string, earth, and 0 work again. Okay, it's 0 work in this case because the string is perpendicular to my displacement. So that tension, remember that work is force times distance times the cosine of theta, and that theta is always going to be 90. So the string does no work. Gravity is internal to my system because Earth is part of my system. So I can now do some calculations. Okay, mgh in the beginning is going to equal 1/2 mv squared. Okay, I can cancel my masses again because I didn't give you that. And I find out that I have 10 times 0.02 meters. That's going to equal 1/2 v squared. And plugging that into my calculator, I find out that it is moving at a relatively slow 0.63 meters per second. Okay, so that's the speed of my pendulum at the lowest point. Part B brings us back to our circular unit because it's asking, now that I know the speed at the bottom, pendulums make a circular arc. Okay, so at the bottom, I'm going to have the force of gravity, going to have the tension force up, and I will be accelerating towards the center of my circle at a rate of v squared over r. Okay, the rest of it I'm going to let you do at home, and we'll talk about it in class. Hopefully we haven't forgotten circles. We just covered them after all, but hopefully we can solve that at home, and we'll finish it in class. And here's the last example, okay? Roller coasters are great examples of conservation of energy because they really convert the roller coaster car, the gravitational potential energy at the top, into kinetic energy, and that continues on as long as we ignore friction. Okay, so here I have a roller coaster is brought to the top of a hill and released from rest. Okay, so here's my roller coaster. It goes down to the bottom. And my speed here is 25 meters per second. Okay, so now I gave you information about the end. Okay, so here I have kinetic energy, quite a bit of it, let's say, and in the beginning it was all gravitational potential energy. Okay, Earth is part of my system still, so I don't have to worry about that, and the roller coaster car. Okay, the normal force of the track is always perpendicular again, so I can ignore that because of the 90-degree aspect. Okay, so here I have mgh, and that's going to equal 1/2 mv squared. No m, go away. And this is 1/2, I'm going at 25 squared, and that's going to equal 10 times its height in the beginning. And if I do that, I find out that my height is a little over 31 meters. Okay, 31.25 meters. Okay, part B says the hill was actually 40 meters high. Okay, so where did the energy go? The rest of it is how much energy was lost to friction. Okay, it turns out that to calculate, I haven't actually calculated any energies. Okay, the reason I haven't calculated any energies is because I don't have the mass of the car. Okay, because I need to calculate the energies. Okay, I actually need to do mgh and 1/2 mv squared. So I'm going to need the mass of the car. Let's use a number where my mass is going to be equal to 500 kilograms. Okay, so in the beginning, for part B, I had 500 times g of 10 times an h of 40, and that's going to equal 20 plus 1, 2, 3, 4, 2, 3, 4 zeros, or 200,000 joules. Okay, and that's compared to my height of 500 kilograms times 10 times 31.25, and that gives me 156,250 joules. Okay, and the difference there, I have lost 43,000 750 joules to friction. Okay. Part C lets us get into using force times distance. Okay, the friction is opposite direction of travel. It's kinetic friction. My distance is 80. Average friction force, I'll let you calculate that at home. So we'll talk about that and finish that in class as well. Okay, thank you.